The last couple of topics in statics have to do with centroid or center of gravity. They're similar, right? But they're different. I'll explain the difference later. Now, recall in chapter 7 or 8, we talk about internal forces or friction. You have a rigid body, and the rigid body has certain weight, right? And you draw the weight vector down the middle. Let's say a box or like a simple beam, right? So this weight vector is applied down the middle, and that's easy because, well, the shape is simple, right? What if the rigid body is complicated, right, in shape, like this, right? Then where do you draw this weight vector, right? Is it here or is it down here, right? You need to pinpoint exactly where you draw this force vector, okay? And that's the whole point of this chapter. Centroid center of gravity. It's the location, I call it G, right, where you draw the weight vector, okay, where this weight vector is applied. And that's it. And you have to be able to know the location of this weight vector precisely, because when you take moment of all the forces acting on the rigid body, right, when you take moment about a certain point, then this location, right, becomes critical. Right? So let's learn how to determine the location G of any rigid body. Okay. Now, to study the methods to find centroid or center of gravity, we need to first look at 2D case and then extend it to 3D. Okay. So let's focus on 2D first. So for 2D, we'll be looking at an area or curves. Okay, curves or lines. Right. Now, let's look at area. Okay? And let's first look at center of gravity. Okay? Let's develop some equations to find center of gravity. Okay, that is the location of center of gravity, and then I'm going to continue on to find the location for centroid and compare the two, right? Just to see if there's any difference. Okay. Let's say we have a simple shape like this. Okay, it could be a round, could be an oval shape, it doesn't matter, right? Some rigid body, right? Two-dimensional. But in order for me to formulate the equation, let's add a little thickness. Right? It's a thin plate, right? So a small little thickness called H. Okay, a little height. Now, I would like to determine this location G of this area. Okay. Now, I have defined the coordinate system X, Y, and Z, and this area is lying on the XY plane. Okay, so Z plane is going perpendicular to this surface right here. Okay, so this H is along the Z plane. So the whole point of this is to find X bar and Y bar. And here's the standard. We use X bar and Y bar, okay, and Z bar later when we talk about 3D. Okay, we use the overhead bar to represent the location, the coordinates of center of gravity. Okay, represented by this point called G. Okay. Okay, so now we have this set up. I'm going to take this same thing here, except now I'm going to split this simple area into tiny, tiny little elements. Okay, I'm going to decompose it into a million of pieces, like this. Okay, so divide it into many simple elements, okay, tiny elements. Now, each element right here, it's a surface, it's a tiny surface, okay? So each surface has its own weight, right? And we add all the weight together of these each individual tiny pieces, then you end up with the total weight, right? So for each individual weight, okay, of the element, I can draw the location of this weight vector of this tiny element. Okay, so element 1, remember that. Element 1. So the weight of this element is W1. Okay? And I know exactly where it is because this element is so tiny, right? The area it's almost like a point. Right? So I know exactly where this is located. Right? So you can do the same for any other element. Right? So this element, you can draw another vector straight down. So W2 is this element 2, right? So, so the sum of all these elements, okay, the weight of the element, will become the total weight of this rigid body as a whole. Okay? So I can very quickly then write down the equation for the weight. So if I write down this W, okay, where W is total weight, right? And just simply apply through this point G, and here is where I draw the weight vector. Okay? So this W right here is equal to the sum of all the individual weights. Weight 1 plus weight 2 plus, and so on. Okay? So let's say we divide into n elements. Okay? N is some huge number, right? It doesn't matter here. Okay? Now when you take the limit, W becomes the integral of dW. Okay? So this relation, okay, will be equivalent to these two pictures right here. Right? The total weight applied through this point G, which is the center of gravity, is equal to the sum, right? The integral of each of the individual weights. Okay? All right. Now here's the key. Okay? Now we take moment. Take moment about x-axis and y-axis. Okay, so we'll take moments twice. All right, first take moment about x-axis. The moment of this picture on the left has to be exactly the same as the moment on this picture right here. Okay, so the moment of this whole piece, okay, having a weight of W, right, about x-axis, has to be the same as the moment of each and the individual piece about x-axis as well. Okay, that is the sum of all the moments. Okay, so so what now we can do is develop two equations. For sum of the moment about x and y axis. Now, about x and y axis. And let's do this. Sum of moment. Take y axis first, and then sum of moment about x-axis. Alright? So the sum of moment, this is my x-axis, this is my y-axis. Okay? So some moment about y-axis, I recall from previous chapters we talked about moment, right? Summing moment about an axis is equal to the moment arm times the force vector. In this case, the moment of the weight vector. Okay? Moment of this weight vector, W, about x-axis, or y-axis first, right, is the moment arm. In this case, that's exactly my x bar. Okay? So some moment about y-axis, okay, for this rigid body as a whole is your x bar times W. Right? So this is your moment about y-axis. Okay? But that's also equal to, right? So when we split this into a million tiny pieces, okay, so each piece has its own weight. Okay. So, so the total moment, okay, about y-axis is equal to sum of the moment of each individual piece. And the moment arm for each piece, right, draw this, and that is my x to y. The moment arm that is measured from the y-axis to this location of the element, I'm going to call it x tilde. Okay? Recognize the difference. This is x tilde and this is x bar. Now x bar, the overhead bar, is reserved for the center of gravity of the entire rigid body. Okay? Tilde, the overhead tilde, okay, is reserved for the coordinate of the location of the individual element. Okay? So this is the center of gravity of the whole thing, and this is the center of gravity of the individual pieces. Okay? So this equals x tilde 1 times W1. So that's the moment of this tiny piece about the y-axis. Just keep going. Okay? So x tilde 2 times W2 plus so on. Okay? Until you sum up everything. Okay? Same thing for y-axis. For x-axis. So that's y bar times W equals y1 tilde times W1 plus and so on. Yn times Wn. Okay? So where y bar is this location right here, right, this coordinate, and y tilde is the y coordinate of the individual elements.